Okay, so I'm going to talk about our project at Cambridge and Cranfield on increasing the life of marine turbines by design and innovation. And the basic aim of this project was to reduce unsteady loading to eliminate fatigue problems. And basically what we're trying to do is break the link between the highly unsteady inflow and the thrust and torque that is applied to the turbine. So as we saw some quite cool videos of this morning, the tidal channel flow is fairly unsteady. We've got surface waves, the actual boundary layer of the channel, roughness from the seabed and upstream geographical features that mean that the turbine sees a highly fluctuating, from the point of view of the blades, a highly fluctuating incidence. And that generates unsteady lift and drag on the blades. Now what happens then is that's obviously passed right through the system. So the blade experiences a fatigue load, the gearbox experiences a fatigue load, and the pylon will also experience load fatigue. And eventually you're likely to lose one of those components. So in order to understand this problem, we've had to go from upstream of the turbine and the actual flow in the channel, through the unsteady hydrodynamics on the blade itself, downstream to the drivetrain itself. And this afternoon even, I'm going to talk about some of the work we've done on turbulence measurements and modelling, and some of the work that we've done on the actual gust alleviation itself. For those of you who've seen this stuff presented before, the major additions in the past year have been that we've been to Ifremer for 2 weeks and tested out some of the ideas that we previously had only had in the lab or in a wind tunnel. So first of all, turbulence measurement and modelling. The piece of work that we've done at Cambridge on this has been to develop a novel probe. It's a 5-hole probe based on an aerospace technique of measuring pressures to find flow speed. And we built a prototype and tested it at Ifremer. It's here, and that's a Vectrino, and that is the LDV system at Ifremer. This is Mark 1, which turned out not to be much of a fan of water, but Mark 2 was a bit more successful. So this is some power spectral densities that we got. The red lines are the probe and the black lines are Ifremer's LDV system. And you can see we captured the wave, when we had the waves on at 0.5 hertz, we captured that quite nicely. And when we didn't have them on, we didn't capture it, which is good. And we get a very similar roll-off as the frequency goes up. As well as measuring the turbulence, this is some work that Cranfield have done on how you would then use your improved knowledge of the flow in a simulation. They've developed a novel inflow generator for open foam. And the idea here is that you can put much more anisotropic and inhomogeneous turbulence into your solution, into your simulations. So the comparison of the sort of inflows generated with a standard code and the Cranfield method are shown here. I personally don't know much about how they achieved this, but they assure me that there are 2 papers in preparation that they can point you in the direction of if you want to know more about that. So then once we know what's going into the turbine, what we want to do is, as I said, break the link between this unsteady incidence and the forces going through the structure and the drivetrain. And we've got 2 strategies for that. First of all, try and control the flow on the blade such that the unsteady incidence doesn't generate unsteady lift and drag, or allow that unsteadiness to pass through the system by allowing the drivetrain to respond more quickly. So in both those cases, we did some tests in the lab at Cambridge or Cranfield, and then we tested the concepts at Ifremer. So in Cambridge, we were looking at the blade flow control, and we built a gust tunnel to generate an unsteady incidence variation in the wind tunnel. So this here is an incredibly expensive Venetian blind that generates sinusoidal incidence variation that we can change the amplitude and frequency of. So we tested out a few concepts for flow control in the wind tunnel. And we were able to show that using a few different techniques we could deploy devices that would drop the lift for a given angle of attack so that we could have constant lift over a range of angles of attack. Then came the fun bit of trying to fit that same mechanism into a 0.75 metre diameter turbine for testing at Ifremer. So you can see we've got, from the CAD, we've got a mechanical actuation system, and then also in here was an Arduino and various microprocessors. And we were able to get Wi-Fi communication between this rotating part of the turbine and the surface of the water, which enabled us to change what we were doing without taking the turbine out of the water, which was helpful. So that's a picture of it with one of the devices on being tested at Ifremer. So we tested 3 devices, but broadly speaking we had some devices that could control thrust. So this is a plot of the datum thrust TSR curve of the turbine, and then when we deploy the device we drop the thrust, or device 2 where we deploy the device and we lose power or torque. So these were steady experiments showing that you could alter for a given tip speed ratio either the torque or the thrust. Then we wanted to know whether you had any chance of doing any actual load control with these. So what we did was we switched the waves on in the tank to generate unsteady flow at the hub height, and the waves were going at half a hertz. So we turned the devices on to 0.55 hertz such that they would go in and out of phase with the waves. So if the mechanism works, what we should see is over 11 cycles we should see them doing exactly the wrong thing and amplifying the fluctuations, and then doing exactly the right thing and attenuating them. So this is what we got for the thrust device. So here we have the fluctuations in thrust beating as the device goes in and out of phase with the waves. So this part of the cycle is exactly what you don't want, an enormous fluctuation, and this part is exactly what you do want, a much smaller fluctuation. So broadly speaking, looking across our data, we think we can get about a 50% reduction in the loading, which would be pretty significant in terms of fatigue life if you could halve the thrust fluctuations on your turbine. So secondly, we looked at drivetrain control. And again, Cranfield had the same strategy as us of testing out on a bench in the lab and then verifying at Ifremer. So first of all, they started with a pair of back-to-back motors, so one acting as a fake turbine and one acting as a generator, to look at different torque control schemes. And they put data in from NREL's FAST program to simulate the turbulent response of a turbine. They then replaced one of the motors with a actual turbine, 2-bladed turbine, and still kept this low inertia system so that they could simulate different inertias through their MATLAB Simulink and LabVIEW control scheme. So this is 2 of their results. So they tried constant torque, which is the blue fluctuations, and then they had a constant RPM control as well. So you can see that with allowing the turbine to change speed enables you to keep the torque constant to within about 2%. If you want the RPM to stay constant, you can, but you get these much larger fluctuations. So to conclude, we've the major achievements over the last year have been in 2 areas. We've developed a probe to improve turbulence measurements, and also developed a way of getting some slightly more realistic turbulence into open foam. And secondly, we've been testing our load alleviation devices at Ifremer, and we've shown torque or thrust control via the blade, and also control via the drivetrain itself. So thank you.
This production is brought to you by the University of Edinburgh.